Hello, and welcome to another session of chemistry. Our focus today is Unit 11, Day 3, which is about neutralization reactions and titrations related to acids and bases. As it notes, if you haven't already done so, watch the Zoom meeting from today. It gives you a nice little background of and connection to today's topics. Assuming you've done that, let's go ahead and get started. The objective for today is to be able to describe the chemistry that goes on in something called a titration, and then to use titration data to calculate the unknown molarity. So go ahead and set up your EQ. I know it's a little bit of a long one. You can split it into two if that makes more sense. But again, having that EQ at the top of your notes is nice because then it guides you in terms of what you should be thinking about during the notes and what you should be able to do when you're done. And it can help you write your summary. And it's a nice way to process the information from today. All right, let's get into it. So a titration uses the chemistry called a neutralization reaction. So the first thing we're going to do is make sure you know what that is. A neutralization reaction is a reaction between an acid and a base. Always, that's the definition of a neutralization reaction. They are also always double replacement reactions. Again, these are just definitions. So these are things that you'll see every single time. If you've decided it's a neutralization reaction, it will always be an acid and a base, and it will always be double replacement. So let's review that just really quick. So remember, a double replacement is when two things switch spots, and it's because of opposite charges. So in this case, it's showing you that A and C are both cations, positive, and then B and D are both anions, negative. So when they switch spots, B and D cannot go together because they're both negative. A and C cannot go together because they're both negative. And A and B were already together. C and D were already together. So the only option is that A now goes with D and C now goes with B. And notice that, just a reminder, we always put the positive one first, the negative one is second, and then now that creates two new compounds. That's just the standard definition of double replacement. Now, when it's an acid-base reaction or a neutralization reaction, we actually can be a little bit more specific. The products of a neutralization reaction will always be, again, not an exception, always be water and some type of salt. And when we say salt, we're referring to ionic compounds. So not always sodium chloride. It could be sodium chloride, but some type of salt. So let's just already talk about where this comes from. I recommend that you think of water as HOH because then it's going to remind you that water was able to form because acid had an H that broke off and base had an OH that broke off. Well, H's are positive, OH's are minus. So if H broke off of something, that means there's a negative, extra negative floating around. OH is negative, meaning it broke off of a positive. So there's an extra positive floating around. So the negative from the acid and the positive from the base will form your salt compound. And that is every single time, water and some type of ionic compound, salt. So here's just a quick example. So HCl plus CaOH2. Okay, well, we can already figure out that, yep, this is an acid and a base. How do I know? Acids start with H and bases often have OHs. So this fits our just simple definitions of acids and bases. So we know that this is going to be a double replacement neutralization reaction. I told you that it forms HOH every time because the H rips off of the acid, the OH rips off the base, and then that will form your water, H2O or HOH. Then you'll have a Ca left over and a Cl left over to make your salt. You do have to double check. Oh yeah, on the periodic table, Ca has a +2 charge, Cl has a -1 charge. So when those two come together, you'll need two Cls. So it'll end up looking like this. So let's review where that came from. This H came from the acid. The OH came from the base. They make water. Then the two leftover pieces, a Ca and a Cl, make your salt. And the reason we needed two Cls is because calcium has a +2 charge, Cl has a -1 charge, so two chlorines to balance that +2 on the calcium. And then the last piece of it is, a good review here, is that we need to also balance the whole equation because we have two Cls on this side and only one on that side, and that's not allowed. We can't suddenly have more atoms at the end than we did at the beginning. So a hint for these neutralization reactions, always start with your salt and work backwards, and it will just kind of balance itself. So that's just a nice little trick. You can balance it however you want, as long as you get a balanced equation in the end, but I'm telling you that's a really nice hint. So I'm going to start with the salt, two Cls, which means that I would need to put a 2 in front of here, All right, so I have two Cl's now, but then now I also have two H's. And if I go on this side, yeah, there's two H's, but remember, this is really not just an H, it's an OH. So there's really only one H by itself, so I'll need to put a 2 in front of there. Oh, but then that means there's going to be two OHs. Oh, but there already was two OHs on this side. So now that is a balanced equation. So again, it's an acid-base reaction is called a neutralization reaction. It's always double replacement, and you'll always create HOH and some type of ionic compound, which is your salt. The H positive, the OH minus make HOH water. Then you'll have a negative and a positive left over to make your salt. Balance the formula, balance the whole equation. All right, go ahead and do a level 1 question already, and then we'll jump back into it. Okay, so now that you know kind of the chemistry that's going on, we're ready to talk about this thing called a titration. So a titration is a lab procedure that uses neutralization as its main focus. So what we'll be doing is you take a solution that you measured out a certain amount, and you add it to another solution to figure out the concentration. So you've got two solutions, you add one to the other to figure out the concentration of the unknown. So one of the solutions you know everything about. What is it? What's the concentration? How much did you use? The other solution, probably all you know is maybe what it's called, but maybe not even. You don't know the concentration, but you could measure how much you use. So that'll be kind of the data. So before we get into the details of this, I just want to give you kind of some connections of why we use this. Titrations are often used when you're trying to test something that you don't know how strong it is. So for example, when I worked at General Mills, we would smash up food samples and we would test the acid content of certain foods, such as fruit snacks was a really common one, because fruit snacks, if there's too much acid in them, it would taste too sour, people wouldn't like it. If there's not enough acid, it would be bland, nobody would like it. So we would do titrations on smashed up solutions of fruit snacks to figure out the acid concentration in those fruit snacks. It can be used in water testing. So if there's something in the water testing, if you're testing for the level of acid rain, you could definitely do that. Take a water sample, titrate it, and you could figure out the concentration of acid in that water sample. Or you could use it for other contaminations. It's used in a lot of different medical testing. So it could be used for different bodily fluids to check for things that either should be in there at a certain concentration or things that are not allowed to be in there at a certain concentration. So medical testing would be another place that it's used. And sometimes titrations can be done with machines. Titrations, the way we're going to learn them, would really only be useful if you're looking at like a really specific project, something that you do over and over again. A lot of times machines will do those titrations. But it's good to know what's going on so that you understand what those machines would be doing. So that's kind of a little bit of connection of what titrations are for. All right, so this is generally what a titration setup looks like. You would generally have two of these, one for the known solution and one for your unknown solution. So here's a couple of the terms that we use when we talk about titrations. The standard solution is the solution you know everything about. You know what it is, you know the concentration of it, and then you would measure how much you use. And then that would be that you have to have a standard solution. The other term that's important is called the endpoint. And it's called that because it's when you stop your titration. So it's the end of your titration. And what's important about it is that it's when you have neutralized. So if you're doing an acid-base titration, the endpoint is when you stop, because you're neutral at that point, meaning you can use your balanced equation to figure out your chemistry answer. The endpoint signals, this is what I just said, it signals the point when the balanced equation is true. So whatever reaction you're doing between acids and bases, that endpoint says, hey, stop here, because right now the data that you have matches your balanced equation. And then you can use that data to solve the problem that you're trying to solve. And we'll get into that in just a little bit. So those are a couple of the main terms. Once you kind of know the terms, what I want to do next is talk about the steps of a titration. So again, this is kind of the setup. A lot of times you would have another one of these for your acid. So this is set up for your base. This is called a burette. funnel so you don't spill because it's a really small opening. You've got a dispenser here. And then the acid could be the thing that you don't know the concentration of. So when you're doing a titration, you start by measuring out the solution with the unknown concentration, and you put it in an Erlenmeyer flask. Now, I do want you to think a little bit about why an Erlenmeyer flask. So an Erlenmeyer flask, remember, has a specific shape. It's different than a beaker. So why do you think this shape with this setup might be better? And it turns out that it's because the shape of it, kind of like a triangle, it prevents stuff from splashing out. So as you're adding stuff, if it splashes, it's going to splash on the sides and then go back down into your mixture. And that's important because different drops can affect your data and your final answer if it were to splash out. So that's the purpose of the E-flask, the Erlenmeyer flask. After you measure your unknown solution, then you're going to add an indicator. In this case, it says a tablet indicator. It could be a liquid. It could just drops of it. And the indicator, if you remember from a couple days ago, an indicator is a chemical that has a chemical reaction with the H's or OHs in the solution, and it changes color so that we can see. There's a whole bunch of different kinds of indicators. You choose a specific indicator that works with your chemicals that you're dealing with. So you would choose, that's why it says an appropriate indicator. So you want to find one that changes colors at a neutral point, or if you're adding a base to an acid, you would want to, it would change color when there's base present. That's not necessarily when it's acid. So different things that you can choose. Okay, so you measure your unknown, you add your indicator, and then using this thing called a burette, you turn the stopper here, and that measures your standard solution. So in this case, the base would be our standard solution, the unknown is the acid, and we're gonna add base, turning the stopper, add it until you get to that endpoint. And again, the purpose of the endpoint says stop, your balanced equation is true. How do you know you're at the endpoint? Well, that's because you chose a specific indicator. So here's a visual. For the lab that we're going to do, we're going to use an indicator that turns pink when it's basic. So the starting point would look clear. So this is your unknown acid with a little bit of indicator in it, but it's clear right now. As you add, you can see that the pink is starting to stay a little bit. So that's when you start to slow down because the pink is showing you that there's a certain amount of OHs in there for the indicator to react with. So you're close to your endpoint. The light pink, when the whole thing stays pink, that's your endpoint. If you get a dark pink, it would show that you overshot your endpoint. And that could matter because your data is not really at the neutral point anymore, and that can throw off your calculations. So again, the idea is that you measure out your unknown, you add an indicator. You measure how much base you use, which is your standard solution in this example, and you're going for that super light pink in the whole solution, not when it just is pink for a little bit, because this is going to swirl away. And if you get too pink, then you've passed your endpoint. All right, so those are your steps of a titration. Our next thing we're going to do is, okay, what do we do with our data? But go ahead and do a level 2 question right now, kind of thinking about maybe explaining the steps of a titration or summarizing them. Okay, so then now let's imagine you did that. You did that lab with the titration. And we'll show you next what do you do with that data. So you had a data table set up like this. You would know that how much did you start with on your burette, on your acid. You would just measure that. Notice it doesn't have to start at 0. You would measure what was the starting volume on your base. Then you added a bunch of acid to your Erlenmeyer flask. So the final volume was 37.16. You added a bunch of base during the titration. You got to that neutral light pink endpoint, and then this was the final volume of your base. So that burette was that long skinny thing, so that's where these numbers came from. So the first calculation you do is you need to figure out how much acid and base you actually used. This isn't how much you used, this is just where the level was when you started. This is not how much you used because it didn't start at 0, right? So just a quick subtraction. So to figure out how much base you used, you would take the final minus the initial, and then you'd get, that's the milliliters of base you used in this trial. Same thing for acid, take the final minus the initial, and then that's the amount of acid that you used in this trial. So now those are the numbers we're going to use moving forward. All right, so here's that example again. So we put 35.01 milliliters of our acid. I know it's the acid because it starts with H. It's neutralized by 15.13 milliliters of a 2.0 molarity base solution. This is our standard solution because we know the concentration of it. What we're trying to figure out is, well, what's the concentration of the acid? So the lab technique got us the data that we needed to be able to figure out the concentration of this acid. And that could be useful for some sort of like drug testing or testing the acid content of a lake, or it could be, again, it could be like a food sample. Like, is there too much or too little of this acid in it? Okay, so we already have our two volumes. The next thing we need to know is we need to know the balanced equation. So for this balanced equation, we know that our acid is the H3PO4. We know that the base is NaOH. So start with that. We know, because of the first thing we did today, that it's neutralized. This is an acid-base neutralization reaction. So H and OH will make water. Na with a +1 will bond with PO4 with a -3. That means I need 3 NAs to balance the PO4, and then I have to balance the whole equation. So let's check it here. Here's the acid, here's the base. Water and some type of salt. Start with the salt and balance the whole equation. 3 NAs, so I need a 3 right here, 3 NAs. Now there's 3 OHs, but I already have 3 OHs here, and then 3 H's here, 3 H's here. Okay, so that was the first thing we learned how to do today. Balanced neutralization reactions. Acid, base, water, salt. Balance the charges on the ionic compound salt, and then balance the whole equation. So now I have our balanced equation. The next thing that we're going to try to figure out is we're going to try to figure out moles of base. Let me actually back up for a moment. We're trying to find the concentration of the acid, and we're going to do concentration. This concentration is molarity, so that's going to be what we figure out for the acid concentration too. So that means I need moles of acid over liters of acid concentration. Well, I have milliliters of acid, which I can turn into liters, but I don't know anything about the moles of acid. However, from my balanced equation, I know that there's 3 moles of base for every 1 mole of acid. So if I figure out the moles of base used, I can figure out moles of acid. That's the big picture. That's where we're going. Okay, now let's go back into little steps. Because I know the molarity of the base, I can figure out the moles of base. So if I start with my milliliters and turn it into liters, and then times it by my molarity, liters will cancel. I'll be left with moles. Okay, so again, let's see where that came from. The amount of base used was my starting number. I turned it into liters because molarity was given. 2 molarity is really moles per liter. So then everything cancels except moles. You multiply those numbers, divide by 1,000. We end up with 0.0302 moles of NaOH. And don't worry about sig figs yet because this isn't a final answer. Okay, so then now I've got my moles of NaOH. But remember, the goal is molarity of acid, and molarity is moles over liters. So then now that I have moles of base, I can use stoichiometry, balanced equation ratio, to get from moles of NaOH to moles of acid. So now I can calculate the moles of acid neutralized. So start with this number. The balanced equation says that there's 3 moles of NaOH for every 1 mole of H3PO4. And again, that came from here. Watch where I'm going. The 3 came from this coefficient. The 1 is implied. If there's no number there, there's really 1. So it's a 1-to-3 ratio. So really, I take this number divided by 3. That gives me my moles of H3PO4. Notice that it's helpful to have everything labeled. So we knew that the NaOH goes on the bottom, so it cancels. The acid on top, because that's what I'm looking for. And you end up with somewhere around 0.0100 moles of H3PO4. Okay. Concentration is being measured in molarity, which is moles over liter. Well, now I have my moles of acid. Now I can calculate concentration of acid. Remembering that it's moles over liter, so this goes on top. And then I've got my 35.01 milliliters. If I divide that by 1,000 milliliters, that will get me to liters. So really moving the decimal 3 spots. So my molarity of my acid is moles of acid divided by liters of acid. This number, moles of acid, came from the previous question. And this 0.03501 came from taking the milliliters from your data table, divided by 1,000, so that milliliters cancels, and then you get it to liters. And then now we want to focus on sig figs. This has 4 this has 4, but this only has 2. So our final answer rounds off to 0.29 molarity. So then now, as a chemist, we would figure out if that number is too high or too low, or if it's just right, and then you would analyze the data. But this is the calculation. So let's review. We took our data and figured out milliliters of both acid and base. We had a balanced equation, and then we used the given molarity and the given, we'll calculate it from our data table, from the lab, the milliliters of base, and we were able to get moles of base. We used stoichiometry to convert moles of base to moles of acid, and then the definition of molarity is moles of acid over liters of acid solution, moles of acid over liters, which came again from our data table, and then we got our final answer using sig figs. So the cool thing about this, what I get really excited about, is think about all the chemistry this reviews. It reviews writing equations, balancing equations, dA, moles, stoichiometry, molarity. So many topics in this one problem. And if this is making sense to you, you can be so proud of that. And if it's not making sense, it's just because it's brand new. You will get it. This is what your lab is going to be about tomorrow. There's also some unit practice problems if you want to see more examples like this, to try them and check your work. Or of course, you can look at stuff online if you want to. But the good news, it's the same steps every time. Start by getting your milliliters of acid and base, balanced equation, moles of whatever molarity you have, moles of the other thing using the ratio from the balanced equation, and then moles of the whatever you're looking for and liters of whatever you're looking for to get your final concentration. And that's it. Go ahead and do a level 3 question, summary for today. And then that's the end of day 3. So here's what I'd like you to do before we finish up today. Finish your constant questions and summary if you didn't already do those. There is a practice assignment that just practices writing neutralization reactions. It doesn't have any titration calculation stuff on it because that's going to be tomorrow's lab. But the neutralization reactions, just practicing that. There is a practice assignment. Try to get that done today and submit it. There are some unit practice problems that have a bunch of stuff from today, especially titration calculations, which might be nice if you need to see more examples before you're ready to do tomorrow's lab. And then that brings us to the end of today, and I will see you at our next Zoom meeting. And I will give a plug. Our next Zoom meeting, we will be doing another titration calculation example together. So if that was still a little bit tricky to you, you obviously can ask me questions, but know that during our bell ringer tomorrow, we will be doing or at our next class, we'll be doing a titration calculation again as an example. All right, thanks so much for joining in. We'll see you next time.